Today we're going to talk about special quadrilaterals. But before we do that, we need to go over some vocabulary. The first refers to adjacent sides. Two sides of a polygon are adjacent if and only if they have exactly one vertex of the polygon in common. So if you look at this diagram, this segment and this segment are adjacent sides because they both share this common vertex. So this segment and this segment are adjacent, here and here. These two, they're here and here. These two are adjacent, and here and here. These two are adjacent. We also have adjacent angles in every polygon. Two angles of a polygon are adjacent if and only there is exactly one side of the polygon that is a subset of both angles. So in this case, if you look at this angle here and this angle here, they're adjacent. Sometimes in traditional textbooks, they refer to those types of angles as consecutive. There are several types of special quadrilaterals, and we have to be very, very cautious about the definitions because some of the definitions vary from book to book. So the defining conditions of the various categories of special convex quadrilaterals are as follows. In our book, a trapezoid has at least one pair of opposite sides parallel. In some books, it has exactly one set of opposite sides parallel, but we consider any quadrilateral with at least one pair of opposite sides parallel a trapezoid. The next category is that of a parallelogram. Parallelograms have both pairs of opposite sides parallel. A kite, they have two disjoint pairs of congruent adjacent sides. Disjoint means two pairs are disjoint if and only if no member of one pair is also a member of the other pair. Isosceles trapezoid is a trapezoid with two disjoint pairs of congruent adjacent angles. A rectangle has all four angles congruent. A rhombus has all four sides congruent. And a square has all four angles congruent and all four sides congruent. So in this case, a square is both a rectangle and a rhombus. So in EMF, we look at different kinds of quadrilaterals based upon the number of reflective symmetries they have. In the first category, these quadrilaterals have no lines of reflective symmetry. A quadrilateral having none of the special features mentioned on the previous page has no lines of reflective symmetry. A parallelogram that is neither a rhombus nor a rectangle has no lines of reflective symmetry. A trapezoid, but not an isosceles trapezoid, has no lines of reflective symmetry. In the next category, we have quadrilaterals with exactly one line of reflective symmetry. Those quadrilaterals are a kite but not a rhombus, has one line of reflective symmetry. An isosceles trapezoid but not a rectangle has one line of reflective symmetry. Some quadrilaterals have exactly two lines of reflective symmetry. Those are a rectangle but not a square, has exactly two, here and here. A rhombus but not a square has exactly two, here and here. A square has exactly four lines of reflective symmetry through the vertices and through the sides. Now you may have noticed that in the last page I said a rectangle and a rhombus, not a square. That's because a square is always a rectangle and it is always a rhombus. So let's take a look at the next page here. So we've got to put it all together and we've got to know our quadrilaterals. If you look at this diagram, you can see I have convex quadrilaterals. Within this category, I have trapezoids that have at least one set of parallel sides. So within the category of trapezoids, I have also isosceles trapezoids that has exactly one set of parallel sides with the non-parallel sides being congruent. And trapezoids are also parallelograms because parallelograms have two sets of parallel sides. Then an isosceles trapezoid could also be a rectangle because a rectangle has two sets of congruent sides, opposite sides congruent. But it also has at least one set of parallel sides. So you can see all these definitions overlap somewhat. So in here, if we look, a rhombus is a parallelogram, but it's also a kite. A kite has two disjoint sets of congruent sides. And if you look at a rhombus, all the sides are congruent, and therefore it's also a kite by definition. But again, you always have to be very careful about the definition in various books because some books will say a trapezoid has exactly one set of parallel sides. Some will not allow a rhombus to be considered a kite, and so forth. But in our EMF book, this is how these all fit together. So let's look at the definitions a little bit more carefully. A trapezoid has at least one pair of opposite sides parallel. A parallelogram has both pairs of opposite sides parallel. A kite has two disjoint pairs of congruent adjacent sides. An isosceles trapezoid is a trapezoid with two disjoint pairs of congruent adjacent angles. A rectangle has all four angles congruent. A rhombus has all four sides congruent. And a square has all four angles congruent and all four sides congruent. So in this context, every trapezoid is a convex quadrilateral. We can see that's the case. Every trapezoid is a convex quadrilateral. Every kite is a convex quadrilateral. Every isosceles trapezoid is a trapezoid. Every parallelogram is a trapezoid. And now looking at this diagram, I'm going to give you some questions that are sometimes always never questions, and I want you to think about it. So here I have 6 statements that I want you to answer as sometimes true, always true, or never true. I want you to pause your video and answer. When you're ready for the answers, press play. Here are the answers. A rectangle is an isosceles trapezoid. Always, a rectangle has at least one pair of opposite sides parallel, and it has congruent base angles. A kite is a rhombus. Sometimes, a kite's a rhombus if all the sides of the kite are congruent. A rectangle is a parallelogram. Always, opposite sides of a rectangle are always parallel. A rhombus is a square. Sometimes, that rhombus is a square if all the angles of the rhombus are congruent. A trapezoid is a kite. That happens when the trapezoid is a parallelogram, which is a rhombus, and therefore a kite. Not all trapezoids are kite, but sometimes they are. A square is a rhombus. That happens always. Squares always have opposite sides parallel and all sides congruent. Here's an example of a 2-column proof that shows that every rectangle is a parallelogram, and also a paragraph proof. The paragraph proof is on the left. So in our paragraph proof, it says, let PQRS be a rectangle as shown below. PQRS. Notice as we name our quadrilateral, we never skip vertices. We can go counterclockwise or clockwise, but we cannot skip a letter. So from exercise 108, we know that QR is perpendicular to RS. Let's mark that. QR is perpendicular to RS, and we know that RS is perpendicular to PS. Hence, QR is parallel to PS. Similarly, QP is parallel to RS. Hence, PQRS has both pairs of opposite sides parallel and is thus a parallelogram. Now, let's look at the two-column proof that's on the right-hand side. So PQRS is a rectangle, that's given. The measure of angle QRS is 90 degrees, and the measure of angle RSP is 90 degrees. Therefore, we know that QR is perpendicular to RS. These are all true by definition. We also know that RS is perpendicular to PS, and that's true by definition. Therefore, we know that QR is parallel to PS by definition. Lots of definitions here. The measure of angle PQR is 90 degrees. That's true by definition. QP is perpendicular to QR, definition. QP is parallel to RS by definition, and therefore PQRS is a parallelogram by definition. Traditional school books have different types of definitions for these quadrilaterals, and even between different publishers, there are different definitions. So whenever you read any books, you have to pay very close attention to the definition. But I'm going to show you the most common definitions for each of these types of shapes. The first is that of a rectangle. It is a quadrilateral with 4 right angles. Next, we look at a square. A square is a quadrilateral with 4 congruent sides and 4 congruent right angles. A kite is a quadrilateral with at least 2 pairs of congruent consecutive sides. Now, be really careful between books, especially with kites. Some books, some traditional books, allow a kite to be a rhombus, and some do not. A trapezoid is another figure where not all books agree on the definition. Some say it's a quadrilateral with exactly 1 pair of opposite sides parallel, while others say it's a quadrilateral with at least 1 pair of opposite sides parallel. In our book, we allow a trapezoid to have at least 1 set of parallel sides. Here's some more information about a trapezoid. A special trapezoid is an isosceles trapezoid. A trapezoid in which the non-parallel sides or legs are congruent. So if we look at this figure here, we have different pieces. We have bases, those are the parallel sides, and then in addition, the non-parallel sides we call legs. In an isosceles trapezoid, the legs are congruent. In an isosceles trapezoid, the 2 parallel sides are the bases, and the pairs of consecutive angles whose common side is a base are a pair of base angles. Sometimes they only refer to the lower pair as the base angles if the bases are drawn horizontally. But truly, most books I've ever seen have this as 1 set of base angles and this as another. In an isosceles trapezoid, each pair of base angles are congruent. If a trapezoid has each pair of base angles congruent, then it is an isosceles trapezoid. In EMF, this is a part of the definition of the isosceles trapezoids. Our next EMF theorem is called the diagonal betweenness theorem, and it says this: let pi be a plane and let G be a convex polygon with at least 4 sides. Let A, B, and C be vertices of G such that segment AB and BC are sides of G. Segment BC and AB are sides of G. Let X be any other vertex of G. So I've let this be X. Then the ray BX here is between BA and BC. And then in addition, the ray XB here is between XA and XC. Here is the first part of the proof for the diagonal betweenness theorem. It goes like this: let pi G, A, B, C, and X be as described in the statement of the theorem. By the convex polygons in half planes result, C, X, C, and X are elements of the half plane determined by AB that contains C. So remember, the half planes theorem says this: if I have vertices C and X, say here, and I look at the half plane determined by AB containing C, all the vertices are on one side of that line from my convex polygon. So I have C and X, they're elements of the half plane determined by AB containing C. I'm going to get rid of this for right now so we can see things a little bit more clearly. Then by the betweenness in a half plane result, either BC, ray BC, is between BA and BX, or BX is between BA and BC. That's betweenness in a half plane result. Suppose that BC is between BA and BX. Here's BC, and of course in this picture, it's between BA and BX. Then by the betweenness of points in rays result, BC intersects segment AX here, and a point P, say, that is between A and X, here and here. By the points of the same open half plane result, this means that A and X are in different open half planes determined by BC. Here's my line BC. A and X are in different half planes. But since A and X are vertices of G that are different from B and C, the convex polygon in half plane results assures us that A and X are in the same open half plane determined by BC, namely H sub BC comma A. Here. This is a contradiction. Therefore, we must conclude that BX is between BA and BC. Here's BX. It has to be between BA and BC. Next, I'd like you to work on exercise 107 for part 2 of the diagonal betweenness theorem. Press pause on your video, and when you're ready for the answer, press play again. Here are the answers for exercise 107. Again, the diagonal betweenness theorem proof, part 2. So we're going to let pi, g, a, b, c, and x be described in the statement of the theorem. By part 1, we have that bx is between ba and bc. You'll notice that I have it drawn over here. By the betweenness of points and rays result, it follows that bx intersects segment AC. So here's bx and intersects segment AC, and a point P, say, that is between A and C. We must now show that P is not equal to X. So we suppose, on the contrary, that P is equal to X and look for a contradiction. Since X is a vertex of G, it is one endpoint of two sides of G. Let the other endpoint of one of the sides be the vertex Y. There are two possibilities. One, Y is an element of AC. So the first subcase says that Y is equal to A. So you've got to imagine that Y is point A over here. So then A, that is Y, X, that is P, and C are distinct vertices of G that are collinear. But we know from convex polygon checklist 4 that C belongs to an open half plane determined by x, y, and is therefore not collinear with x and y, and there exists my contradiction. Subcase 2 is where y is not equal to a. Then a, x, that is p, and y are distinct vertices of G that are collinear, but we know from convex polygon checklist 4 that a belongs to an open half plane determined by xy and is therefore not collinear with x and y, and there exists my contradiction. Now let's look at case 2. Y is not an element of line AC. Then xy is not equal to AC, and they intersect in the single point x, that is P. Since A and C are not elements of xy and x is between A and C, we have that xy intersect AC is not equal to the empty set. By the points of the same half-plane result, this means that A and C are in different open half-planes determined by the line xy. But by convex polygon checklist 4, both A and C are in the same open half-plane determined by line xy, and there exists my contradiction again. Since we reach a contradiction in both cases, we must conclude that P is not equal to X. Hence, X is not an element of line AC. It then follows by the betweenness of points and rays result that ray XP is between XA and XC. But ray XP equals ray XB, and our result is established. Now I'd like you to work on your homework. Your homework assignment consists of EMF 16, exercises 108 through 110. I also would like you to work on a Delta Math triangle angles and proofs assignment that you can find on the Delta Math website.